Hello and welcome back. In this video, we'll study an important property of a prime number of the form 4k plus 1, which means that its remainder when divided by 4 is equal to 1. For all such primes, there exists an integer such that this integer squared plus 1 is divisible by p. This is not the case for primes of the form 4k plus 3. So this is what differs primes of the form. Primes which have remainder 1 when divided by 4 from the primes which have remainder 3 when divided by 4. We start the proof from Wilson's theorem. Which states that for any prime number p, p minus 1 factorial plus 1 is divisible by p. We will not prove Wilson's theorem right now, but we will give several proofs later, and none of these proofs will use our today's corollaries, so we will not have logical cycles here. Okay, so we'll use this statement. We understand that p minus 1 factorial is the product of all integers from 1 to p minus 1. Well, we simply substitute p minus 1 by 4k in this expression here and write down this factorial. 1 multiplied by 2 multiplied by and so on, and in the middle of this big product we will have 2k minus 1 and multiplied by 2k and multiplied by, I need to go to the next line, multiplied by 2k plus 1 and multiplied by 2k plus 2 and so on until we reach the end. In the end we will have 4k minus 1 and multiplied by 4k. And this is p minus 1 factorial. We need to add 1 and we will get something divisible by p. Well, okay. Now notice that 2k minus 1 is actually p minus 2k. Okay, well, 2k plus 2 is actually p minus 2k minus 1. Well, indeed, just check. 4k plus 1, if we add one to another. This will continue. In the end, we will have p minus 2 and finally p minus 1. So just notice that we subtract from p 2k, 2k minus 1 and so on to 1, the same numbers, the same integers as in the product above. This means that if we transform the lower part of the product, it can be transformed into, well, we have quite plenty of p's here, and why don't we just take all the p's outside of the brackets and there will be something inside. It really doesn't matter what will be inside, because all that matters is divisibility by p. So something divisible by p, and besides this we'll have the part that does not contain p, but the only way to gain a product which doesn't contain p, is to take the second part in each of the expressions. So 2k from here, well, actually minus 2k from here, minus 2k minus 1 from over here, and so on, minus 2 from over here, and minus 1 from the last expression. And the product of all these expressions is either plus or minus 2k factorial. And we understand that there is an even number of minuses, 1, 2, 3, and so on. All in all, 2k minuses. So the product will be sign plus. And the upper part of the factorial is actually equal to 2k factorial. Well, this is simply 2k factorial. This allows us to notice that, well, this part is divisible by p, and this is 2k factorial, and this is also 2k factorial. So this means that 2k factorial multiplied by 2k factorial is divisible by p. Oh, sorry, plus 1. Don't forget about this. Plus 1 is divisible by p, but this is a square. So finally, if we take z equal to 2k factorial, then we will have z square plus 1 divisible by p. So we have proved what we wanted to prove, and in the end I would just like to emphasize that, of course, z equal to 2k factorial is not the only such z. There are infinitely many such integers z, but here we can take particular integer, and we know that it will fit into this statement.